All right, today we're going to pull back the curtain on the real engine behind AI like ChatGPT. It's this incredible piece of tech called the Transformer. It has completely, and I mean completely, changed the game for how machines understand language. So, let's get into it and see how the magic really works.
I mean, you've probably played around with it, right? Maybe you asked it to write a silly poem or summarize a long email. And it feels like magic, but it's not. It's all thanks to a very specific and frankly, brilliant architecture. So the real question is, how on earth does a computer go from just a bunch of letters on a screen to writing something that actually makes sense?
The secret, as you can see, is something called the transformer. And that's exactly what we're going to unpack today. We're going to break this thing down piece by piece so you can see exactly how it ticks. Seriously, by the end of this, you'll get the fundamental ideas that make all this crazy modern AI stuff possible.
Okay, so here's the plan. We'll start with AI's magic ingredient, then figure out how to turn words into math. After that, we'll see how it connects the dots, and then we'll dive into the two big pieces, the encoder and the decoder. Finally, we'll put it all together in the transformer blueprint. Let's do it.
All right, Section 1, AI's magic ingredient. To make all this stuff less abstract, we're going to follow one simple task, from start to finish. We're going to translate the English phrase, let's go, into the Spanish word, vamos. Sounds simple, right? But believe it or not, this little example has all the key challenges that a transformer needs to overcome.
Okay, Section 2, words into math. First things first, we have a big problem. Computers, well, they don't read words, not like we do. They only understand one thing, numbers. So our very first job is to figure out how to take our phrase, let's go, and turn it into a language the machine can actually speak.
And we do that with something called word embedding. Honestly, you can just think of it like a super sophisticated dictionary. It takes every single word, or token as it's often called, and translates it into a unique list of numbers. So let's becomes one string of numbers, and go becomes a totally different one.
But wait a second. Just turning words into numbers isn't going to cut it, because word order is everything. Look at this example. Squatch eats pizza. Fine, makes sense. But pizza eats squatch, that's a whole different story, right? The exact same words, but a completely different and kind of terrifying meaning.
So how do transformers solve this? With a really clever trick called positional encoding. Basically, on top of the numbers that represent the word itself, the model adds another set of numbers. It's kind of like giving each word its own unique GPS coordinate in the sentence. This little mathematical signature tells the model precisely where each word is, first, second, third, whatever. It's a brilliant way to bake the sentence's structure right into the numbers.
Okay, Section 3, connecting the dots. So right now, our machine has numbers for words, and it knows what order they're in. Great. But what about context? If I say, the pizza came out of the oven and it tasted good, how does the model know that it is the pizza and not the oven? That's the next big puzzle.
And the solution to this puzzle is the absolute beating heart of the transformer. It's a mechanism called self-attention. This, right here, was the massive breakthrough. It's what lets the model understand how words relate to each other across a whole sentence, something older AIs were just terrible at. It's all about weighing the importance of every word in relation to every other word.
So how does this self-attention thing actually work? Well, it's a four-step dance. For every single word, the model creates three new vectors, three new sets of numbers, a query, a key, and a value. Think of it like this. The query for one word goes around and asks the key of every other word, hey, how relevant are you to me? This creates a similarity score. Then based on those scores, the model blends together the values from all the other words. It's literally a process where every word looks at every other word and figures out how much attention it should pay to it.
Okay, I know what you might be thinking. Queries, keys, values, why all this complexity? Why not just use the original numbers for the words? It seems like a lot of extra steps, right? It's a totally fair question.
Because this is where the magic happens. This whole process gives each word a new representation that's soaked in context from the entire sentence, and it gets even better. They can stack these attention mechanisms on top of each other. It's called multi-head attention, which lets the model look for different kinds of relationships all at the same time. It's like one head might be tracking verbs and subjects, while another's tracking the overall sentiment. It's incredibly powerful.
All right, Section 4. We've just talked about the essential building blocks, right? We have word embedding, positional encoding, and the star of the show, self-attention.
Well, you put those things together, and you get the first major part of the transformer, the encoder. Its whole job is just to read and deeply understand whatever you give it.
So when we feed our little phrase, "let's go," into this encoder, it chews on it using all those tools we just talked about. And what comes out the other end isn't a word. It's a rich, numerical representation, a bunch of numbers that are packed with information about what "let's go" means, in what order, and how the words relate.
Now there's one more little detail that's super important, something called residual connections. You can think of it as a bypass lane on a highway. After the data gets processed by a layer, like self-attention, the model adds the original, unprocessed version right back into it. It's a simple trick, but it's crucial because it stops the model from forgetting the original information as it goes through all these layers. It makes training these giant networks actually possible.
Okay, part 5, the decoder. So our encoder has done its job. It's thoroughly understood, let's go. Now it's time to hand that understanding over to the second half of our dynamic duo, the decoder. Its job to actually generate the output we want, the word vamos.
So how does the decoder work? Well, it looks a little familiar. It starts with a special start of sentence signal. It has its own self-attention layer, just like the encoder, which helps it keep track of the words it's already said. But it has a crucial new piece that the encoder doesn't have, a special connection back to the input.
And this new piece is called Encoder-Decoder Attention. This is the bridge between understanding and generating. It lets the decoder, right before it spits out a new word, look back at the encoded sentence from the first step. It's like it's asking, okay, based on "let's go," what part should I be focusing on right now to pick the next Spanish word? This is what keeps the translation, or any output actually, relevant to the input.
So, after all that attention work is done, a final processing layer takes over. It takes this rich, context-aware bundle of numbers and makes a choice. It looks at its entire vocabulary, every single Spanish word it knows, and picks the one that is mathematically the most likely to come next. And in our case, boom, that word is vamos. But here's the cool part. It doesn't just stop there. For longer sentences, the decoder takes its own output, the word vamos, and feeds it right back into itself as input for the next round. It keeps doing this, generating one word at a time, in a loop, until it finally predicts a special end-of-sentence token. That's its cue to stop, telling it the job is done.
And that's basically it. Section 6, the Transformer Blueprint. We've just walked through the whole journey, from an English phrase to a Spanish word. So let's zoom out one last time, look at the whole shebang, and quickly recap the key pieces that make it all possible.
So let's nail this down. Word embedding turns words into numbers. Positional encoding tells the model the word order. Self-attention is all about finding relationships within a sentence. Encoder-decoder attention connects what the model understood to what it's about to say. And those residual connections, they just help the whole thing train without falling apart. Each piece is a clever solution, but when you put them all together, you get a system that can finally start to grasp the insane complexity of human language.
So from a simple translation to writing an entire essay, the transformer architecture is what gives machines the power to understand not just words, but the relationships between words. It's a fundamental leap forward. And it really just leaves you wondering, now that machines can master the very structure of our language, what on earth will they learn to do next?